So for the construction of medicines, which part of the body do the medicines typically target? Like,
Let me give you some examples of the kinds of medicines that are biopharmaceuticals and what they're used for. I already mentioned insulin, right? And are you familiar with insulin?
oh yes,
Yeah, so most people are. So insulin is used to fight diabetes, right?
right.
And so if your body doesn't produce enough insulin, which I believe is produced in the pancreas, then you have to add supplement to that. More popular ones are medicines like Humira and Enbrel and Remicade, and those three medicines are all used to fight rheumatoid arthritis, which is a very common ailment, and that's a common way to treat that ailment is through those biopharmaceuticals. There are many kinds of biopharmaceuticals that fight different cancers. For example, there's a medicine called Herceptin that is used in the fight against breast cancer, so it's used to treat breast cancer. There is a medicine called Avastin that is used to fight a variety of different cancers. So the biopharmaceuticals, most of them are protein. That's the kind of molecule that they involve. They're also referred to as protein therapeutics, but they are able to treat a variety of different kinds of diseases.
What is the method of determining which medicines work and do not work?
You first discover a medicine, all right, and that field is called drug discovery. Then you would run some tests to determine whether your drug is effective or not. But if your medicine shows promise, then what you're going to do is to take your medicine into what are called clinical trials. So what you do in clinical trials, and there are different phases of clinical trials, but that's when you have to produce some of your medicine, and you have to give it to patients who are suffering from the disease that you are trying to treat with your medicine. And then you take a lot of data from those patients and you observe them, and you try to make a determination as to whether or not your medicine is safe and it is efficacious. And what that means is it effective? Does it do what you think it should do? So, for example, does the insulin that you're making, does it really treat the diabetes like it should? And so you have to get answers to those questions through clinical trials. And if your clinical trials don't go well, then your medicine won't make it to the consumer. If your clinical trial goes well, then your medicine is going to be available as a commercial product. And most of the medicines we're talking about are prescription, right? You get by prescription, not through over-the-counter purchase.
What inspired you to be interested in chemical engineering?
When I was in high school and I took my first chemistry class, I think I was probably a junior in high school, I thought that chemistry was really interesting, and I got very interested in chemistry, and I knew that I also liked math. So probably one of my teachers, maybe my chemistry teacher, suggested that I look into chemical engineering, since as a chemical engineer you have to know both chemistry, right, and you have to know math, because engineers use math to help design processes and to help scale them up to produce large-scale quantities of chemicals or medicine.
Right.
So it was kind of my interest in both chemistry and math that drew me to chemical engineering.
What specific part about it did you enjoy? Was it that you were good at it, or that it was fun, or what?
I liked it, and therefore I was good at it, right? So the fact that I enjoyed chemistry and I enjoyed math and I just enjoyed learning those concepts kind of made me, I was very willing to spend time on those subjects and to study hard and to learn the ideas. So I became very good in those classes, but I think it was because I really enjoyed learning that material. So the two things kind of go hand in hand. I liked it, and therefore I learned it well, and I was good at it.
How do you use chemistry in your daily life outside of the lab?
chemistry is all around us, right? I just told you about the biopharmaceuticals that we make. So people use medicines. We use medicines all the time, both the kind that I described and the more traditional pharmaceuticals that are all made through chemistry or biology,
Mm-hmm.
or biochemistry maybe is a better way to put that. But then just, things that maybe you don't even think about. For example, I'm driving in my car right now, and one of the things that you need to make a car work is antifreeze.
Mm-hmm.
And antifreeze is ethylene glycol, and that's a chemical that some chemist figured out how to make ethylene glycol, and a chemical engineer learned how to make it, or figured out how to make it at very large scale, so that all of us consumers could buy ethylene glycol for our automobiles, right?
Mm-hmm. Right.
So that's an example of a chemical that people use frequently. And there are many others. When you fertilize your yard in the spring, the fertilizer is a type of chemical that's good for your grass.
Mm-hmm.
And so somebody has to figure out how to make that. It probably involves a chemical engineer. Even when you pump gas into your car, that gasoline comes from oil that's extracted from the ground, and then you have to figure out how to basically separate the gasoline from that heavy from that heavy oil. Mm-hmm. And that's something that chemical engineers do frequently. There are a lot of chemical engineers who work in the petroleum industry. So those are all kinds of things that related to chemistry and chemical engineering, mm-hmm. that we use all the time, and that we kind of take for granted, I think.
Yeah. So you mentioned fertilizer uses chemicals to treat plants and enhance them. Do you know how specifically or what specific chemicals are used to treat those?
For example, fertilizers usually contain a lot of nitrogen. Mm-hmm. And I'm not sure specifically what chemicals are used to do that, but it's all nitrogen-based chemicals.
Okay, so so for sorry.